Okay, hello guys, and welcome to the basics of calculus. So, in order to be able to do those questions in that class, you need to know a little bit of calculus. So, the only thing you really need to know is what is a derivative and what is an integral. So, I guess first, I'm assuming you know what a function is. So let's draw a little thingy here. So like a function, for example, is like f of x. Or another example of a function is like y. And this is like y equals. And then this function, for example, here on the left is the function is f, and it is a function of x. And then this function on the right here is a function y. And how you know what this function is a thing of is, for example, we have y equals t squared plus 1. So in your class, you're only going to have one type of variable in the function. And so this is a function y of t, just as this is a function f of x. So that's what functions are. And so a derivative, the derivative is an operator that you use like on a function. So the derivative of y, you write it like this. And derivative is something you do on a function. So this is t squared plus 1. In that same way, an integral is also an operator that you do on a function. So the integral of y. Because y is a function of t, we have dt in our integral. And this is what sort of an integral looks like. It's that curvy shape. And the thing about integrals is they can also be closed integrals, but you don't really have to worry about that in your class. So a closed integral is just something that looks like this. And so it is the integral of this function within the range 0 to 7. So t squared plus 1 is a function that looks like this. This here is 1. And then the integral is from 0 to 7 in this range. It is the integral of this function. So then let's answer the question of what is a derivative and what is an integral. Like, what does it actually do to our function? So let's start with the integral, since I already have this photo drawn. What an integral is the area under the curve of a function. So if we look at this integral above this one, which is the integral from 0 to 7, it is this area right here. So say you say you just had a function that's like a straight line, and you have the interval 0 to 4, and this is the height of 2. You can literally figure out the integral of this function by calculating the area under here, because this is very easy to calculate, right? It's just 4 times 2. That's the area of a rectangle. But say you have a shape like this, it becomes a lot harder to calculate this area. And so that's why an integral is very useful, because you are able to figure out a function to get this area. Or it gives you the area even, when you have like the bounds like this. But then with a unbounded integral, like say we were going back to this guy here, then it would be the area under the curve for like up to infinity, negative infinity to infinity, whatever that area is. But it gives you a function to figure it out with the bounds. Okay. Maybe we went a little bit too deep, but it is just the area under the curve. That is what is a integral. So then what is a derivative? We're going to look at this guy right here. And the thing with derivatives is they can be written two ways. So say you have this formula here, equation. Y prime would be equal to the derivative of y, which is equal to the derivative of t squared plus 1. And these should actually be t, but because the parameter is t. So those are just some notations for how you might see derivatives. So let's say we have the function y equals t squared plus 1. Okay, I'm back. I got some water. So, now let's look at what is a derivative. So we're looking at the function y equals t squared plus 1. Which is right here, because remember that what derivatives and integrals are operators that we use on functions. And so what the derivative operator does is it gives us a new function that tells us the slope at every point of this function. So just very quickly, let's go into what is the slope of a function. And what does that really mean? So the slope, a good way to see it is the rate of change of a function. So say that this function describes your position, which we usually denote as x. If we were to get the derivative of position, think of what is the rate of change of position. Rate of change is like you have 2 units, so it could be miles per hour, for example. Keep that one in your head. Or meters per second, even more importantly, keep that one in your head. But it could be really anything. It could be people per second. Could be what could it be? I don't know. It's a rate of change, so the rate of something happening. And so if we were to get a rate of change of position is usually given by meters, rate of change for position would be meters per second. And that's just something that, I don't know a good way to explain that, but it's always just seconds when you're working with meters, because it's like the rate of change is more about like how fast you can go per time. So it could be like kilometers per hour. That's a rate of change, because it's kilometers is your change, your position, and then kilometers per hour is the rate of that position. So then if we were to take a look at the slope of this at every single point, we have, all of these tiny slopes at every point. And turn that into a new function, which I will draw over here. So a good way to draw this, and this is just for your understanding of what a derivative is, you're never going to actually have to draw it like this, is let's take a look at like some key points and then look at the slope on our original function. And then let's put in our slope into our new formula, or new function. So this we'll call y prime, which we said was the derivative. Actually, I don't think I said it in this one. I cut it out. So, one way people write derivatives, the main way to write it is this form. And what this is the derivative of whatever function is here. So the derivative of y with respect to t, which is time. And that's where the seconds come from, is because we're doing the derivative in respect to time on position. Because that's like the only useful, rate of change, is how position changes according to time. If you don't understand everything, don't worry. I'm like not saying everything the best way, but so then we have the derivative of y with respect to t. This can also be written as y prime, and you'll see this really often. And so keep that in mind. So in our new function here, we have y prime up here. Our original function is with y. So let's take a look at the slope at 0. The slope at 0, the function is completely flat. So what is a flat slope? Rate of change of this slope at, a flat slope. Like say you have a flat like this. Rate of change can be calculated by rise over run. So height over distance. And so our height is 0 on a flat line. And so our derivative is also 0. But this is only at this point 0. Because when we go to the right, it starts to go upwards, right? And then to the left, it starts to go... we're only moving to the right. So it's just always curving upwards like this, right? And so at 0, we have a rate of change of 0, instantaneous rate of change. Okay, so that's 1 point on our new derivative function. So let's take a look at number 1. At point 1, we can plug into our function. So y of 1 would be equal to 1 squared plus 1, because t squared plus 1, 1, plug it into t, 1 squared is 1, 1 plus 1 is 2. So then we know at point 1, really it should have been like maybe here. We know at point 1, our y is 2. So now we know what slope we're analyzing. We're taking a look at this slope right here. So I would say that this, you could calculate it, but if it was drawn accurately and stuff like that. But since it's not, we're just going to guess. We're just going to say, well, you could calculate it by doing the derivative, but instead we're doing this drawing method. So we're just going to say that it is a slope of around 2, because it's more high t than it is runny, if that makes any sense. Like, it's like higher than a 45-degree angle, it looks like to me. Like, this height is longer than this x. And so we're going to say that that is 2. And so let's go to 1, and let's say that the derivative at this point is 2. So we've put this point here. Now let's take a look at negative 1. So at this point, it should be at it should be at 2. Still here, because this is an even function. It's equal on both sides. So it's kind of very symmetrical, and that is very nice. So what we're going to say here is that it's rise over run, but remember that we are moving to the right. We're not starting from this origin 0 and then moving to the right here and moving to the left here. We're starting from negative infinity and we're going to infinity. And so when we look at this point, our rise is actually negative, because when we're going to the right, the line goes downwards. So we're looking at a rise like this and a run like this. So we have, like, say, negative 2 over 1. And so at negative 1, let's draw that over here. And so at negative 1, we can put at that our derivative is negative 2, because that is the rate of change of our function y at the point negative 1 when we're looking at it at these instantaneous points. And so something that we are seeing that is interesting is that this is looking kind of linear. So we've gone from this very curvy function that, starts off getting is like decreasing, but decreasing by less, decreasing by less, decreasing by less, decreasing by less. And then eventually it becomes flat and then starts increasing slowly, faster, very fast. The derivative of that is starting to look like this straight line. And then I'll do it at this position too. Well, we can't do it because it's not drawn. But anyway, so that's sort of what a derivative is. It's a new function that gives you this instantaneous rate of change of the function. And so, in your class, that is not how you will be solving for derivatives. How you will be solving for derivatives is by using derivation rules, we call it. And so you just it's really fun, actually. There's like a bunch of different rules for different types of functions, and then you kind of just have to know them. But there's a few rules that you have to know to be able to do like pretty much all of the derivatives that you'll ever have to do. And the thing that's good about derivatives is there's never an impossible derivative. It's always possible to do. Which is not the case for integrals, which is very frustrating because you'll spend hours trying to figure it out only to find out that it's not a possible integral with normal methods. And so derivatives are really nice. That's why they're very nice to do. So let's take a look at the function that we have. It's going to be a way to show you two rules of derivatives. So this is our function right here. Let's delete all this. Now, if we take the derivative of this, you'll notice that we have two things in this function. So let's go ahead and write what that derivative, first of all, next step would look like. So we have y prime equals, and then we'll go ahead and write the derivative. And we're doing it with respect to t, because t is our parameter here. And so we'll go ahead and write t squared plus 1 like this. But then we see here that there's two things in our function here. So what should we actually do with this derivative thingy? Well, the thing about derivatives is they are distributive. And so we are able to write this as the derivative with respect to t of t squared plus the derivative with respect to t of 1. So it's kind of like you did a multiplication, right? If this was a 5, for example, instead of d over dt, you could do 5t squared, right? This would be a 5t squared, plus 5 times 1. So this would be a 5 times 1. And so in that same way, that multiplication is distributive, derivatives are distributive. And so we'll write it like this. So that is one of the rules that is important to know about derivatives. Distributive. Let's do this actually. Okay. So then, now you need to get into how to actually do a derivative on a function. So on the right here, we have number 1. Now, this is one type of derivative, derivative, not derivative. So if we have the derivative of any constant, so this is c to represent any constant. This could be e, it could be pi. Something that you'll likely not have to do, but technically is correct. Not technically, it is correct. So because we have the derivative with respect to t, if we had anything with y in it, y does not change in relation to t, and thus this is constant with respect to t, and thus it is a constant in this derivative. But we don't have to worry about that for now. 5 would be a constant. 19 million would be a constant. 44 billion would even be a constant. And the derivative of any constant is equal to 0. Now, what's one way to think about that? The derivative of any constant. Remember, a derivative is something that we do on a function. So what is a function of 0? Let's say, what is a function of c? Let's say y equals c. That is a function of c. It is just a straight line at c. And what is the function that is the derivative of this? Remember, the derivative is a function that gives you the rate of change of this. Well, this never ever changes. There's never a rate of change. And so the derivative of any constant is 0. Okay, so then we can go ahead and do this. This is equal to 0. But what is the derivative of t squared? Now, to be able to do that, you need to know the power rule when it comes to derivatives. So we have the derivative. Since x is over here, we're going to be using x. If I put a t here, t is not in respect to x. And so t is a constant. And so this would be 0. But we're doing x instead, so that the derivative can apply to it. X to the any power, any exponential. This is including x to the 0, which is really this constant rule, but we don't have to go into that. Including x to the negative 8, so x to anything is equal to n times x to the power of n minus 1. So pretty easy to apply. So let's think of what that means to t squared. Now, first thing we look at is t is in respect to t, and so this derivative does apply. Now, we have t squared, and so let's go ahead and look at our xn. Let's pretend this was a t squared. Let's see equals. So this 2 is where the n is, right? So 2 is n. So let's go ahead and put our 2 here. And then our x is really t, so let's go ahead and put t here. And then t becomes to the power of n minus 1. So n was 2, and then let's do minus 1. So this is t to the power of 1. So the derivative with respect to t of t squared is equal to 2 times t to the power of 1, which you don't have to write since it is just t. Let's see here. Oh yeah, okay. So the power rule, essentially what you do is you take the exponent, you times it, and then you just reduce the exponent by 1. So it's really easy. If you were to do that for t squared again, it would be, you take the exponent, so let's say the derivative of this you take the exponent, you times it by the parameter, and then you reduce the exponent by 1. So 2 becomes 1, which you don't have to write since that is just t. Now let's try that with t to the 18. Okay, let's apply the power rule. What could this be? I'm going to give you 5 seconds to figure this out. Actually, I'll give you 10 seconds. Okay, so if you thought to take the exponent and times it by the original parameter and then reduce the exponent by 1, wow, good job. You did it right. So then, now that we know that the derivative of t squared, in order to do that, we're going to say we take the exponent, we times it by the parameter, and then we reduce the exponent by 1, which is 1. And you don't have to write that because t to the 1 is just t. So now we have plus 0. What does this equal? 2t. And boom, all of a sudden you have a function that describes what the rate of change of our original function is. So let's go ahead and delete all of this and draw our functions again. So we have, let's use some lines instead of freehanding it. Okay, so okay, so I'm going to draw our original function, which was y equals t squared plus 1, which gave us a shape like this, drawn better. And then y prime, we just figured out, is equal to 2t. So what does 2t look like? Well, at 0, if you plug in 0 into t, 2 times 0 is 0, or 0. At 1, 2 times 1 is 2. So at 1, our function of y prime is equal to 2. So we put our dot over there. At 2, 2 times 2 is 4. So our function at point 2 is 4. So I'm going to put our dot there. Now, what is our function at negative 1? 2 times negative 1 is negative 2. So it is negative 2. And all of a sudden, 3 dots that are on a line, you know, you have a linear line. And now you're seeing that original shape that we drew just by sort of understanding what a derivative is actually equal to the function that you get when you derive it. And so that is the power rule. Now there's a few more rules, but we don't have to get into those yet because I think I can explain to you the physics without having to explain more of this. And if you run into harder derivatives and integrals, you just have to learn how to do those derivatives and integrals or apply the rules. Oh, we didn't even get into integrals. Oh my god. Okay. All right, let's do integrals. So we said that a integral is okay. Let's see. I'm playing RuneScape on the side, sorry. 449. Okay. So an integral we said was the area under a curve. So, let's draw our function. don't know why that caught me off guard. I knew I was going to have to do integrals. One thing that's very cool about integrals and derivatives is they're like the inverse of each other. It's like multiplication and division. So if you take a function and you integrate it, and then you derive it, you get the original function back, which is pretty cool. And so, if we have y equals t squared plus 1, we said that the integral of that is the area under this curve. Now, the integral doesn't really give you a new function. I mean, it definitely does, but it's hard to put meaning behind that. It's more of easier to be like, okay, this is now the slope of whatever this is. Because if this is the integral of this, that means that the left one, if the right one is the integral of the left one, that means that the left one is the derivative of the right one, since they're inverses of each other. And so what you would do is you would say, oh, okay, so at point 0, my slope is, well, you would start at a very negative part just to figure out like a starting position. You would start at like negative 30, figure out actually, you would have to be given a starting point, because if you're not given a starting point, just the rate of change is not enough to know your exact position. But if you're given just one starting point, then for the previous of it and the rest of it, you can figure out whatever your position is just by knowing the rates of changes instantaneously. So let's say we're given a starting point of down here, which is at negative 3, let's say. So let's say at negative 3, our function, which we're now calling the derivative of our integral, or of our function that we're getting to, this was the function t squared plus 1. So let's say at negative 3, let's plug that into here, we get 9 plus 1, 10. So we're at a position 10, but we're going negatively, we're going downwards. So it's actually a slope. Yes, it's actually a slope of negative 10. Because remember that this is a function that describes what the slope of this function is at any point. But actually then, if we're at 10, that means the slope is 10. So at negative 3, our slope must be positive 10. Yeah. Okay, it took me a second, but... So positive 10 here is a very steep slope. And it gets slowly steeper until we said here that we are at point 1. The lowest slope it gets to is 1, and then it shoots off into infinity again. So this is kind of a bad example to try and show this graphically. But the good thing about integrals is you kind of don't really need to understand them graphically. Just understand that it's the area under the curve, that's what it's telling you. And know the rules of how to do it. And so if we have the integral of our function, which was t squared plus 1 of dt, because remember t is the parameter that we're interested in. If this was a y, this t would be a constant with respect to y. And so this integral would be, you would do it differently. But it is with respect to t. And so what you do is, in the same way that the derivative is distributive, integrals are also distributive. So we can split this up. Because there's a plus in the middle, that's important. It doesn't work with times. It needs to be plus or minus. We can distribute it to these sets of integrals right here. Now, we're going to start with the integral of c. So the integral of c dt, the integral of any constant, so this c could be pi, it could be e, it could be y, remember, because y is not with respect to t. It could be a billion, it could be 5, it could be, I already said that, 1,175. And so all you do, the integral is just the same constant times the parameter that you care, ct. Now, something that's kind of interesting about integrals is, remember how we said they're the inverse of derivatives? We remember that the derivative of any constant is 0, right? And so technically, when you're doing the integral of c dt, you're also doing the integral. This is going to sound super stupid, but it's so important that you're going to be like, this is stupid. C is equal to c plus 0 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 dot dot dot. You know what I mean? And so the integral of c, believe it or not, is actually equal to the integral of c with respect to t plus the integral of 0 with respect to t plus the integral of 0 with respect to t plus the integral of 0 with respect to t plus the integral of 0 with respect to t plus the integral of 0 with respect to t, and so on forever. And so you need to think about what is the integral of 0. And we said that the integral was the inverse of a derivative, right? So one way to think about that is, say we have the inverse of this rule. So what do we have to do to 0 to get c? We have to do an integral. Because remember how I said that if you do a derivative on a function and then do the integral, you get your original function back? So say your original function is c. Then you do the derivative on c and you get 0. So then in order to get c back, you have to do an integral, since that's the inverse of derivative. So you do an integral on 0 and you get your original c back. And so what c is it's any constant. And so that is important to keep in mind, because what any constant means is that if you have so we said that the integral of 0 is equal to any constant, right? So we don't just say that, oh, okay, it's 5, it's any constant. We say c. And so you just have a bunch of c plus c plus c plus c plus c plus c plus c, yada yada. And the thing with c is you can add as many of them as you want. You can subtract whatever number you want from it. It's sort of like infinity, but the idea of it is that it's any constant. You don't really care what it is, and it can be anything. Because, think about it. The integral of 0, you could have derived anything to get that 0. Like, the derivative of 5 is 0. The derivative of 7 is 0. Oops. The derivative of 7 is 0. The derivative of any constant is 0. And so what if I then told you, what if I didn't put this 7 here? What if I didn't put this 7 here? And I said, okay, so then the derivative of 5 is 0. Tell me the integral of 0. Would you be like, oh yeah, the integral is just inverse of derivative, so we derived the 5, and so the integral of 0 must be 5. Would you say that? No, because the derivative of 7, why am I doing it like this? Derivative of 7 is also 0, right? And the derivative of 5 billion is also 0, and the derivative of 5 million is also 0. And so really c is any constant. You don't really care what it is at this point, and it's just c. But it's very, very, very important. If you forget it, it's bad. Because if you don't have the c, you're getting rid of it's like hard to explain, but like see how we're integrating c here and we're integrating 0 here, and the integral of 0 turns into c. So this c is like one dimension higher than 0, like in the world of integrals and derivatives. It's like one step up of power versus 0. Like it holds more info than 0. And so, or like, I don't know what's the best way to say that, but so it's just very important that you don't forget that plus c, because say you were to keep integrating this forever and forever, if you integrate it once, all of these c's combine into one c. The integral of c, remember we said, is c times t. You would get ct plus c, because c times any amount of c's. The reason I drew this is just for you to understand that like you could do it that way and just like really, really blow it up and be like devil's advocate, but just having 1 0 is good enough too. So we would end up with a ct plus c. And so say you want to integrate this again, what do? So all of a sudden, you know the integral of c with respect to t. That's going to be ct. But this now is equal to, you have to do a new integral rule that we're about to learn, ct, plus the integral of c, which we said was ct. So let me draw this all out. And there's no integral here because we've already applied it. And very importantly, we now have a new c. And so if you were to keep doing integrals on this function, you keep getting these new c's. And that is very important, because you're going up the world of integrals and you need to keep adding that c. Okay, all that to explain the very important concept of why you need to add c. So we said that, what did we say? We said a lot of things. The integral of c dt equals ct. Why did I say that? Okay, so the integral of any constant times dt is just that constant times t, because that's the variable, the parameter. And so what we can do is our integral of 1 times dt, we're replacing c with this 1. We have 1 times t, which is t. And so let's go ahead and replace this integral with t, but let us not forget the very important c. Okay, so now we're left with this integral. Now, in order to do this, we're going to learn the inverse power rule. It's just like the power rule you just learned, but in inverse. So, say you have the integral of the parameter raised to any power. This power could be negative. This power could be let me look something up real quick. But I'm pretty sure this power could be anything except for -1, which is the way to think of a negative power is if you have t to the power of -1, it's 1 over t to the power 1. T to the power of -2 is 1 over t to the power of -2. It's like 1 over t to the power of positive exponent. And so t to the power of -1 is 1 over t. And I think that has a different solution. I think that one is a special case. And I'm just going to look that up just to make sure. Yes. So the integral of 1 over t dt is actually ln of t. So the power rule doesn't apply for t to the power of negative 1. Keep that in mind. But it applies for t to the power of negative 2. And so t to the power of n, any integral of that is going to be, let me think for a second. Oh yeah, it's n plus 1. Sorry. I'm thinking of like the very simple way to write it, but we should write it like this. So it's 1 over n plus 1 times the parameter to the power of n plus 1. Now, don't forget the c. Now let's think about this for a second. What is the derivative of 1 over n plus 1 to the power of t, not to the power of times, to the power of t? Oh my god. 1 over n plus 1 times t to the power of n plus 1 plus c. So what is the derivative of that? Remember that derivatives are distributive, so we can do a d dt on the c and this t. But I'm just going to do it all in one step because we're at that level now. Remember the power rule. You bring whatever exponent down, times it by the parameter, and bring the exponent down by 1. So let's do that. Plus c. The derivative of any constant is 0. So that c is just going to become 0. So let's just ignore this for now. So then the derivative, if we're doing the power rule, we're bringing down the exponent and timesing it by our parameter. And this already has this n plus 1 below. Oh, that's another rule I need to explain. Oh my god. Okay. So derivatives and integrals have a very special rule where if you have a constant, you can actually remove that constant and think of that constant as over here, because this d to the dt, let me not explain it. Let's just say that you can do that. So if we can do that, we now have 1 over n plus 1 t, or we'd need a d over dt here. Okay, calculus is more complicated than I thought. T to the power of n plus 1. So let's do the power rule on t to the power of n plus 1. Remember, we just bring down the exponent, times it by the parameter, and then bring the exponent down by 1. So we have n plus 1 t to the power of, and this is all multiplied by this t, to the power of n. But remember, we already took out this 1 over n plus 1, and this is all being multiplied. I have 2 parentheses here. So what is n plus 1 times 1 over n plus 1? I hope you know that they cancel out. So we can go ahead and delete those. And we are left with t to the power of n, which is our original function. So that is our sanity check that we can do when we're doing integrals to see if we are doing them correctly. Okay, so this is the general formula for any inverse power rule, for any integral of the function to the power of n. Okay, so now if we want to do, okay, where are we at? Oh yeah, so we're doing the integral of t squared dt. So t to the power of n, t to the power of 2, so 2 is n. So what our formula tells us is that the integral of t squared is 1 over n plus 1, so 2 plus 1 is 3, times our parameter t to the power of n plus 1. N plus 1 is 3. Don't forget the plus c. So now our whole integral of t squared plus 1 is and we can simplify this by combining our c's, because any amount of c's multiplied together is just c. You could have 5 times c and it's still c, because you don't know what constant you started with. So you don't know what constant 5 times c gives you. You don't know what constant c plus 5 is, because you don't know what constant c is. So c plus 5 would still be c. It's an unknown constant that you don't really care about what it is, but you just care that it's there. So this is the integral of t squared plus 1. And that is the very, very basics of integrals and derivatives. You're going to learn harder integrals and derivatives, like how to deal with e to the power of x. You're going to learn about ln of x. You're going to learn the chain rule. And you might learn a few other rules. But for me to be able to teach you some physics, that's all you really need to know about calculus. And for you to be able to do those questions that you sent me. So do watch this video first and then watch the physics video.